right, so we're going to look at a multi-phase problem, an example problem. It is your required homework problem. It reads, one-dimensional multi-phase. Sammy was riding her bike down the street. She started at the north end of the street and was going to head south. We will consider north as positive. Her friend Mari was going to time how long it took her to go to the end of the street. Sammy can speed up at a rate of 1.2 meters per second squared until she reaches her top speed at 11.3 meters per second. She can then maintain that top speed for 5 seconds before she gets tired. She then stops pedaling completely and just lets her bike slow down to a stop. While gliding, Sammy accelerates at a rate with magnitude of 0.6 meters per second squared. If Sammy starts from rest at one end of the street, and A, how long does it take her to get to the other end of the street when she comes to the stop? And how long is the street when she comes to the stop? All right, so whenever we do a problem of this nature, of course, we are going to identify the object. We're going to examine whether or not we're in multi-phase or single phase and looking at that initial and final time, and then break that time up. So let's get started. So our object, the object we care about, well, that's Sammy and her trek down the street. We start caring when Sammy starts to ride. Okay, so when she starts that beginning of her ride. And we stop when she gets to the end of the street. And in this case, that's when she comes to a stop. Okay, so our initial, instead of saying stop, I'm going to call this final, just for consistency in my method. All right, so comes to a stop at that final. So the question is, does this all happen with one acceleration? Can I just tackle this as a single one-dimensional motion problem? Well, no. We know this happens over 3 phases. So this is all through 3 phases. So we have to remind ourselves, that means I have 3 accelerations. That means I have 3 parts to my problem in this case. So what is phase 1? Well, phase 1 is going from 0, so the initial in phase 1 is the start, and the final is to her top speed. Phase 2, well, that's when she starts at top speed, and it ends when she gets tired. Right? So she stops at that top speed. And phase 3, that's sort of my glide phase. So it starts when she gets tired, and it ends, or final, when she comes to a stop. All right, so those are our 3 phases of motion. And so now we can identify what those phases look like after we draw our picture and define our world. So, what's our picture look like? Well, here she is on the bike, and I'm going to define the beginning location as my origin, all right? And she's going to be heading in the rightward direction. Okay, so let's look at each phase and what information we have. So, our initial and final positions for phase 1, initial and final velocities for phase 1, our acceleration for phase 1, and our time. Our initial and final positions for phase 2, our initial and final velocities for phase 2, our acceleration for phase 2, and our time for phase 2. And our initial and final positions for phase 3, our initial and final velocities for phase 3, our acceleration for phase 3, and our time for phase 3. What information do we have? Well, we know she starts from the location of the origin. So from phase 1 is when she starts to when she reaches top speed. We're not given the final position of when she reaches top speed. I just have to pull up my information again. We're not given the final position. We're actually given her how fast she could go. So we don't know the final position of phase 1. We know that she starts from rest in phase 1. And we know she reaches her top speed in phase 1 of 11.3 meters per second. Just confirming that? Yep. It does tell us what her acceleration is. That's at 1.2 meters per second squared is her rate of acceleration, but we're not given how much time she has. All right, so that's the information we have for phase 1. What about phase 2? Well, we don't know where she starts in phase 2, but we do know it's the end of phase 1. We don't know where she ends in phase 2. Her initial velocity in phase 2, well, that's the final velocity of phase 1. She's going at her top speed. That's a steady rate, so her final velocity of phase 2 is the same as the initial. Well, that means her acceleration is 0. And we're told that she can maintain this top speed for 5 seconds. So we know that her time during phase 2 is 5 seconds. All right, what about phase 3? Well, we don't know where she starts in phase 3, but we do know that it is the same as the final position of phase 2. We don't know where she ends in phase 3. We do know how fast she's going because she's still maintaining that top speed when we start phase 3. And she glides to a rest, so we do know that she comes to 0 at the end of phase 3. And we're told that the magnitude of her acceleration is 0.6 meters per second squared. That's a magnitude, that's only a size, so we have to think about the direction. So we know the value is 0.6. And if I'm moving in the positive direction and I'm slowing down, my acceleration and velocity have to be opposite. So that must be a negative in this case. And we don't have any idea how long that happens. Okay, so this is all the information that we have. Now we want to answer the question, how long does it take her to get to the end of the street? How much time? And how long is the street? Now if we think about how long it takes her, this time, that's really adding up all these times together. So if we want to know the total time, I have to know time 1 and time 2. So I need this value and I need this value. All right. So let's just look at the second half and then we'll attack the first half. So the second question is asking about how long is the street? Well, that's the length of it. So if I start at 0 and I get to the end, I have the length, which means x final 3 becomes the variable of interest in that case. All right, so those are my 2 variables of interest in identifying this problem. So let's start with the first one, this time total. Well, I need time 1, I need time 2, and I need time 3. I have time 2, so we got that. So let's go after, I don't know, time 1. Okay, so we need time 1. So I have to decide which of my pictures is going to be the most, or excuse me, my equations is going to be the most useful. Well, I have an acceleration, and I know my initial and final velocity, so I think if I want to go after time 1, v final is equal to v initial plus acceleration times time is going to give me that most information. So v final is 11.3, v initial is 0, my acceleration is 1.2 times time. And I can solve for time 1 is 11.3 divided by 1.2. So time 1 is equal to 9.4 seconds. All right, so I'm going to pop that in there as a calculated value. All right, I also need time 3. So I'm going to actually change this pink to a blue just to keep my variables separated. So time 3, well, again, I have a velocity and acceleration, so v final is equal to v initial plus acceleration times time. My v final is 0, my v initial is 11.3 plus my acceleration of negative 0.6 times my time. So I bring 11.3 to the other side and divide. So 11.3 divided by 0.6, and I get a time 3 equal to 18.8 seconds. So now I can answer let's put that in there. To remind myself it is a calculated value. I use the color scheme. So my total time is 9.4 plus 5 plus 18.8. And so I get 9.4 plus 5 plus 18.8, 33.2 seconds for part A. All right, how about part B, which is, what's this final position? Well, I want final position. Again, I'm going to kind of change colors a little bit. I want final position, so x final of 3 is equal to, is what I want. So I'm going to use this relationship, x final equals x initial plus v initial t plus 1/2 a t squared. So x final is what I want, x final 3. X initial, ooh, well that's unknown, but I do know it's equal to x final 2. So let's put x final 2 in there. My initial velocity is 11.3 times my time of 18.8 plus 1/2 negative 0.6 times 18.8 squared. I'm just going to simplify this relationship and find that I actually need x final 2. But let's just get that a little bit simplified. 11.3 times 18.8. And we're going to add that to 0.5 times negative 0.6. Oops, forgot my negative there. Boop. Times 18.8 squared. And we get 106.4. All right, so I need x final 2. Okay, well, okay. We can do that. Let's go after x final 2. Again, a little symbol there. So x final 2. Well, that's often the case where I'll use, my go-to is this more powerful equation. So that's x initial plus v initial t plus 1/2 a t squared. So what does that leave me? I have x final 2, which is what I want, equals x initial 2, which I don't know. But I do know that x initial 2 is x final 1. So that's x final 1 plus v initial, which is 11.2, times time, which is 5 seconds. And I have an acceleration of 0, so that term's going to drop out. So I'm left with x final 2 is equal to x final 1 plus 10, what is that, 23? 11.2 times 5. 23 is adding up 56. So I need x final 1. All right, well then, by golly, let's go after x final 1. So x final 1, x final equals x initial. This is my standard that I start with. It's generally most powerful. X final 1 is 0. Oh, sorry, is we don't know. X initial is 0. V initial is 0 times time of 9.4. Well, I don't really care since it's 0. Plus 1/2 1.2 times 9.4 squared. And I can solve for x final of 1. So x final of 1 is 0.5 times 1.2 times 9.4 squared. I get 53 meters. Okay, so that can go in here, which means it can go up here. So I have x final 2 is equal to 53 plus 56, and I get 109. So x final 2 is equal to 109 meters. So I can put that in here, which means it can go up here. I do like to keep my color scheme. So x final 3 is equal to x final 2, which was 109, plus 106.4, and I get 215.4 meters. Whew, a lot. All right, so x final 3 is equal to 215.4 meters. So What did we have to do to solve this problem? Well, we had to identify what we wanted, of course, what that motion looked like, when it started, when it ended. Does it have three phases? Asking ourselves, is there multiple accelerations going on? Are there phases of these motion? And then identifying what those look like. Drawing our picture, of course, setting that origin so we know what everything is referenced to. Putting in the known values, but recognizing that a lot of these known values lead to each other. They're related. These phases are related to one another. And then going after what we want. Our time, we could get relatively straightforward. But our positions, we went after what we want. We wanted x final 3, and that told us we needed x final 2. So we go after x final 2, and that told us we needed x final 1. So we go after x final 1, and we can work our way back. So identifying what you want to know and going after it, it's going to help you not waste time, of course, and also have fewer mistakes as you let the physics identify what you need. All right, good job.